specification patterns taking reuse to the next level. Abstractly, design patterns provide an optimized, reusable solution to many of today's engineering problems. Experience has shown that they are effective tools for sharing best practices and building skills within a project team. However, one problem that has prevented the widespread adoption of design patterns within the electronic verification community is a lack of an easier searchable library of patterns. In this paper, we demonstrate a systematic set of the guidelines for creating and organizing an extendable library of verification patterns that are applicable across multiple technologies, engines, or platforms in the verification space, ranging from the property specification to UVM test bench development, and formal verification, simulation, formal verification, simulation, and emulation. Introduction. What is a pattern? In the process of designing something, for example, a building, software program, or an airplane, the designer often makes numerous decisions about how to solve specific problems. If the designer can identify common factors contributing to drive the solution and abstract the solution in such a way that can be applied to the other similar recurring problems, then the resulting generalized problem solution pair is known as a pattern. Documenting patterns provide a method of describing good design practices within a field of expertise and enables designers to improve the quality in their own designs by reusing a proven solution on recurring problems. In the context of this paper, we define a pattern library as a collection of pattern entries, where each documented pattern entry provides a solution to a single problem. The design patterns originated as a contemporary architectural concept of Christopher Alexander in 1977, and then they have applied to the design of buildings and urban planning. In 1987, Kent Beck and Ward Cunningham proposed the idea of applying patterns on the programming. However, it was Gamma et al., also known as a Gang of Four (GOF), who popularized the concept of patterns in computer science after publishing their book, Design Patterns, Elements of Reusable Object-Oriented Software in 1994. Applying patterns to the verification is not a new idea. For example, Dyer et al. In 1998 initially proposed the idea of codifying the reusing the property specification for finite state verification using patterns. The first et al. In 2004 extended the idea of applying patterns to the general domain of assertion-based verification. More recently, the literature for many of today's test bench verification methodology, such as UVM, often reference various software or object-oriented related patterns in their discussion, which can provide valuable insight into how to achieve better vertical and horizontal reuse for test benches and stimulus and even platform portability with the advent of the hardware-assisted acceleration. Although patterns have been referenced in the context of design verification in numerous conference papers, it is generally difficult to search, reference, and leverage the published solutions these patterns provide since they are distributed across multiple heterogeneous platforms and databases and documented using multiple varied formats. Furthermore, prior work in the patterns applied to the hardware verification problems has been limited in scope by focusing predominantly on the coding aspect of simulation test benches. In this paper, we address these concerns by extending the application of patterns across the entire domain of verification, that is, from specification to methodology to implementation, and introduce a systematic set of steps for organizing and documenting an easily reference to verification patterns library that is applicable across verification engines or platform. Paper organization. The remainder of this paper is organized as follows. In section 2, we provide a recommendation for categorizing and organizing patterns into a library. In section 3, we turn off our focus to a recommended style for documenting patterns and requirements for creating an easily referenced verification pattern library. In section 4, we present a verification pattern example related to various disciplines in the verification space, such as property specification, UVM test bench pattern examples related to the various disciplines in the UVM test bench development and hardware acceleration. In section 5, we discuss other considerations when creating a pattern library and introduce our freely available online verification patterns library, which is based on the systematic patterns creation approach and guidelines as discussed in this paper. In section 6, we summarize our work and discuss future work such as extending patterns into newer and emerging areas of verification, for example, portable stimulus. Section 2 is categorizing and organizing patterns. To facilitate the learning, ease of use, the quick access and searching for verification pattern content, careful thought should go into organizing the library into searchable categories whose pattern solutions are related and exhibit similar characteristics. Although the verification pattern contains in our library extend beyond the traditional patterns used within the software community, we felt it was important to first understand and build on the prior work and went into the pattern categorizations from this domain. The first attempt at design pattern categorization is attributed to the GOF, who proposed the following pattern organization in the context of creating reusable object-oriented software. Object-oriented software, creation patterns, which deal with object creation, structural patterns, which identify a simple way to realize the relationships between entities, and behavioral patterns, which identify a common community patterns between objects. Bushman et al., in their pattern-oriented software architecture book series built on the work of GOF, proposed three broader category levels for patterns. Architectural patterns, for example, layers, MVC, and P2P. Design patterns, for example, GOF proposal and idioms. For example, language-specific patterns like pimple, RAII, and C++. However, Martin Flower in this book, The Patterns of Enterprise Application Architecture, POEA, and points out that the patterns are not just for documenting solutions to code specific problems. They are also useful for describing solutions to how data and system components are arranged and interconnected. Since our goal in creating verification patterns is to broaden the application of patterns beyond the software domain, we decided our categories should align from high level with the digital design and verification process. Hence, we have identified two main verification pattern categories, which should be familiar with to any design and verification engineer working in this domain. That is, specification patterns and implementation patterns as illustrated in the following figure. The verification pattern library, specific patterns and implementation patterns, and across the properties, the order properties, the environment, and the stimulus analysis. 2.1 Specification patterns. Specification pattern provide a solution to notational problems with when defined the design intent. Various forms of specification notations are being explored in the digital design and verification industry today, such as UML, graphs, and property specifications. Probably the most prevalent form of the formally specifying design intent in the digital verification domain through the use of properties, which can be implemented as either assertion or cover properties. However, learning how to specify properties has historically been a challenge, hence for the initial release of verification pattern library. We decided to focus on the challenging of creating properties patterns with the goal of facilitating the use of common solutions to various property specification problems. As shown in the previous figure, our property specification patterns are further organized into two subcategories, which is based on the work on Dwyer et al. And the subcategories on occurrence properties and order properties. So the occurrence properties patterns require that either some state of or event must occur. For example, universality property patterns or an existence property patterns, or not occur. For example, an absence property pattern. An alternative order property patterns constrain the order of the state and event, and a precedence pattern property patterns or response property patterns. More complex and compound properties can be built up from the combination of more basic occurrence and order patterns contained in our library. So in section 5.1, we demonstrate the occurrence pattern from our library. 2.2 Implementation patterns. The implementation patterns provide solutions to a construction problem for various verification infrastructures. Since the construction of contemporary test benches are essentially large software projects, so with the utilized object-oriented features found in the system Verilog and UVM, so a lot of prior work and software patterns in applicable to the verification implementation patterns. In fact, many of the patterns referenced in the prior verification publications originated from the set of the reusable software object-oriented patterns proposed by the GOF, for example. Factory pattern, abstract factory, and singleton. Polish nerve object, the polish pattern, strategy pattern. The analysis port and analysis component, observer pattern. The phase, template method pattern. TLM, common pattern, a command pattern. UVM object and component to registration, proxy pattern. UVM underscore top and a singleton. The object wrappers adopt or wrapper pattern. However, verification is more than just creating test benches. Hence, our category of implementation patterns is intended to cover a broader set of solutions to commonly occurring problems involved in verification, such as stimulus and analysis. So we have further organized our implementation patterns into the following three subcategories, as illustrated in the previous figure: environment, stimulus, and analysis. The environment patterns are those data used in the test bench architecture, construction, configuration, and communication and synchronization. For example, facade is a facade pattern or component configuration pattern. These patterns are ones that capture the structure and behavior aspect of a core verification environment model. The stimulus patterns capture the behavior, strategy, and types of stimulus. For example, layering sequence pattern. Similarly, analysis patterns are used to capture the behavior, strategy, and types of response checking and coverage. Working pattern, and for use, analysis and stimulus has no interaction or interdependency. The environment test bench includes the infrastructure, interconnect, resource sharing, synchronization, and so on. As such, it touched both analysis and stimulus. It is the structure in which both analysis and stimulus reside and operate. 3. A template for documenting verification patterns. When creating a pattern library, it's important that each documented pattern follow a consistent form and style. This consistency simplifies learning and facilitates ease of use, and when reviewing different patterns contained in the library, the documentation for a verification pattern should describe the context in which the pattern is used, a problem within this context that a pattern is seeking to address, and a suggested solution. Historically, no single standard format for documented patterns exists. Rather, a variety of different formats have been used to different pattern authors. One example of a commonly used documentation format is the one used by a GOF and their book, Design Patterns. However, previous pattern documentation proposal focused on the software pattern. We found that there are other necessary pattern documentation requirements that are specifically related to verification patterns and that are not addressed by previous proposal, such as documenting specification patterns. Hence, our verification pattern template extended previous software pattern documentation proposal to address a broader set of requirements related to verification. 3.1 Verification pattern template. Our verification pattern template consists of following sections. Pattern name, a unique descriptive name that helps in identifying and referencing the pattern. Intent, a very brief description of the goal behind the pattern and the reasoning for using it. Motivation, a description of a specific scenario consisting of a problem and a specific context in which this pattern can be applied. Think of this as a problem statement that describes a concrete example. The solution to the problem will be discussed in the subsequent implementation and example sections. Applicability, situation in which this pattern is usable, the language context for the pattern. Structure, requirement for implementation patterns and optional for specification patterns, abstract graphical representation of the pattern. For example, UML class diagram, interaction diagram, and etc. The implementation, a description of implementation of the pattern, the solution part of the pattern. Example, a code or a pseudocode example of how the pattern can be used. It suggested that the example addresses the original problem scenario presented in the motivation section. Scope recommended for specification patterns and optional for implementation patterns. A scope defines the exact extent of the verification execution over which pattern must hold. More property scope detail will be discussed in section 3.2. 3.2. An example is provided in section 4.1. Consequence, optional, description of the result, side effect, and trade-off caused by using this pattern. Related patterns, optimal. Other patterns have some relationships with the pattern, with the discussion and the differences and a similarity between the related pattern. Contribution, identification of a person and their references for this pattern, contribution to the library. For the novice pattern creator, there is often confusion related to the difference between the section, intent, motivation, and applicability. The intent section is generic and high-level description of the problem being solved, and it should be limited to one or more sentences. However, the motivation section is a description of a specific example of a problem where a solution is needed without describing the solution, and it does not need to be brief. Note that motivation section is sometimes labeled the problem statement in other proposed pattern templates. The applicability section will then generalize the specific problem example described in the motivation section so that the reader understands how the proposed pattern can be applied for other similar problems. Finally, we recommend that the example section demonstrate the solution on the same problem previously described in the motivation section. 3.2 Section 3.2 Specification, Patterns, and Property Scopes. First et al. Documented 16 patterns in their book Assertion-Based Design. However, a recent and deeper analysis of these patterns revealed that the base property for a number of pattern examples had a similar implementation, and the main difference between these patterns were often due to the boundary enabling and fulfill condition that delimited the base property. This resulted in a slightly larger set of documented patterns that are necessary. Furthermore, in some cases, it was difficult to see how the example for specific property specification could then be generalized to address new specification problems. M. Dwyer et al. Proposed an elegant solution to the specification patterns generalization problems by defining the property scopes, where the scope defines the extent of verification execution, that is, a design model execution in the simulation, emulation, or a formal verification over which the base patterns must hold. The advantage of defining scope is that it greatly simplifies the process of documenting property specification patterns. So since it generalized the application of a base pattern problem solution paired to many other similar, yet slightly different problems, and thus they greatly reduce the amount of required documentation. Hence, we have adopted the concept of property scope when documenting property specification patterns released in our library. We use the figure below to help illustrate the concept of various scopes for property P and each potential boundary enabling and fulfilling the condition Q and R respectively. Experience had shown that there are 5 common scopes as shown in the following figure that cover many properties related to digital design, which are global, the entire verification execution that is under consideration. Before, if the R occurs, the verification execution up to not but not necessarily including the fulfilling condition R. After the verification execution including and after the enabling condition Q. Between, if R occurs, then a verification execution including and after the enabling condition Q, and up to, but not necessarily including the fulfilling the condition R. After until the verification execution including and after the enabling condition Q and up to, but not necessarily including the fulfilling condition R. The difference between the between and the after until is the scope where the between scope of P only applies if the fulfilling the condition R occurs after the enabling condition Q. However, the after until scope of P applied after the enabling condition Q even if the fulfilling condition R never occurs. Scope extent of the model execution over which the property P holds. Global P, P before R, P after Q, P between Q and R, P after Q until R. So to note, that instead of defining a much larger set of scopes for what we found to be last common instances, where the property P does not overlap with the enabling condition Q, or instance where the property P is required to overlap with the fulfilling condition R. It's easy to extend our smaller set of scope to include these conditions by coding the property appropriately. For example, qualifying the enabling condition Q to prevent overlap with P, or qualify the fulfilling the condition R to ensure overlap with P. Pattern scopes are not necessarily applied to the overall property. That is, often a scope is applied to the a property that is used to form a more complex overall property. For example, sequence underscore express is than the property expression, where the pattern scope might be applied to the sub-properties, property underscore expression versus the overall property. Section 4 is pattern example. Due to the space limitation, we have chosen to present 3 examples from our library in this paper, which each example is representative and of patterns from the main categories contained in our library, specification and patterns and implementation patterns. Section 4.1 is specification pattern example. The following example demonstration our documentation approach for specification patterns and how property scope and can be used to a powerful tool to generate the implementation of a specific specification pattern solution to the alternative form, which is that are used to address a different specification problem. Pattern name: forbidden sequence property pattern. Intent: the forbidden sequence property pattern is used to specify portion of a design model verification execution that provide a specific sequence of designated stage or event. Motivation: in the normal verification execution of an RTL model, there are often specific sequences of stage or event that must never occur. This classic example of applying the forbidden sequence property patterns related to checking the fairness in an arbiter. For example, if a specific client A issues a request to the arbiter and the arbiter issues a sequence of multiple grants to client B before the client A is issued a grant, then the arbiter is not fair. Applicability. And a sequence of states or events that describe the undesirable behavior in a design can be formulated into forbidden sequence property. The implementation, the forbidden sequence property patterns can be expressed using any of industry standard specification languages such as SVA or PSL. The following tables has been created only to provide a better understanding of the semantic of forbidden sequence property patterns for our 5 basic scopes, where a scope is a stand of a model verification execution over which the property must hold. The example described in the following table illustrated one instance of a forbidden sequence property pattern that specifies a sequence of 3 low to high T transition is forbidden. For this example, Q, R, and T are Boolean expressions. The property scope and definition, blah 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 blah. Example 1, let us consider fair the to-client arbiter as illustrated in the figure below, where signals request 0 and request 1 are input request to the arbiter from client 0 and 1, and gent 0 and gent 1 are output grants, respectively. For our example, our request is defined as a right H occurrence for either request 0 or request 1, and similarly for a grant. There are the footnote. This is to client arbiter. For our to client arbiter to be fair, a client with a pending request should never have to wait more than 2 arbitration cycles to receive a grant, where an arbitration cycle is the interval between issued grants. In another example, if client 0 has pending a request and a grant is issued twice to a client 1 before a grant is issued to a client 0, then the arbiter is not fair. The following waveform illustrated this failing case. The clock request 0, gent 0, and gent 1, and client 0 has a pending request, yet grant was issued twice to client 1. We can create a sequence represent the condition where the 2 grants are issued to a client 1, and throughout this sequence, no grant is issued to a client 0 as follows: GNT 0, not gent 0 throughout the rows gent 1 to 2, next 2. The following forbidden sequence can be used to construct our fairness property. For this case, we specify that the client 1 should never be granted more than 1 grant when we have a pending request from client 0. Similarly, we can write a separate property to specify a fairness with respect to client 1. For example, the p underscore arbiter arbitrary underscore fair underscore 1 underscore 0. Alternatively, we could create a parameterized property that could be used to check for any pairized arbiter grants I, j as follows. This parameterized property could then be used to fully specify any end client arbiter. A system value generated statement could be used to efficiently create the full set of the properties using this parameterized property. The scope for a forbidden property pattern is our previous fairness in property example is after. Obviously, depending the property we should do specify the forbidden sequence property pattern is the applicable to other scope. For example, global, before, between, or the after until. The consequences. The forbidden sequence property pattern does not specifically require the occurrence of any number of instances for a given state or event. Rather, it forbids the number of occurrences. A property needs to be written if we want to specify a specific number of occurrences are required. Related patterns. The first forbidden sequence property pattern is classified as specification pattern with a sub-classification of occurrence pattern. This pattern is special case of the absence property pattern. Section 4.2 Implementation pattern exampled. The following are two verification pattern examples that are demonstration how we document the implementation patterns. The first example demonstrates a pattern targeted at both emulation and emulation, while the second example demonstrates how to share. The first example demonstrates a pattern targeted at both emulation and emulation, while the second example demonstrates how share the resources between sub-objects without requiring detailed knowledge of the resources. The pattern name, the BFM proxy pair pattern. Intent, the BFM proxy pair pattern is categorized as an environment pattern and facilitated the design of transducers like drivers and monitors for dual domain partitions test benches that can be used for both emulation and emulation and across the verification engines or platform is general. In general, motivation. In order to enable the promote of verification process that is abstracted from the underlying verification engines, particularly a software simulator and hardware emulator. Modern test benches should exhibit from conception a dual domain architecture with partitions HVL and HDL module hierarchies and targeted for the simulator and emulator, respectively linked together run into unison. Fundamental to this architecture is the employment of BFM proxy pairs to be divided so-called split transducers, where the component in the HVL domain typically implemented as a classes act as proxies to BFMs to implemented as interfaces or modules and the sensitizable HDL domain. An HVL proxy provides a surrogate and placeholder for associated cross-domain HDL BFM to control access to it via a transition-based HDL communication model using remote function and talk task calls. Effectively, the proxy embodies the transducer API to offer the test bench layers, abstracting the cross-domain communication and implementation details of the BFM's both cycle state machines. Applicabilities. The BFM proxy pattern is applicable in any situation demanding on a common dual domain partitions test bench architecture that is separated HVL and HDL modular hierarchies in both simulation and emulation and across verification engines in general. Structure. The diagrams below they illustrate the dual domain test bench architecture and according to the UVM agent structure, respectively, with the transducers depicted as BFM proxy pairs. As pairs interfaces pins. And that is implementation HVL tops and HDL tops. Implementation. A trend is following the prescribed BFM proxy pair pattern implements a BFM as a system value interface or a module with dedicated functions and tasks to be called from a class proxy through a virtual or DPIC interface to execute bus cycles, set parameters, or get status information. Additionally, a BFM interface or a module may call functions defined in the class proxy via proxy object backpointer mechanisms to provide a notification of transactions and other interesting events and conditions for control and analysis. Transaction-based cross-domain communication thus enables in both directions, with either the HVL proxy or the HDL BFM as initiators. Each proxy BFM pattern is regarded as a joint pair representing a single transactor. Example: BFM proxy pair pattern source code example for UVM driver and monitor are provided below. The consequences: the dual domain partitions test bench architecture enabled by a BFM proxy pair pattern offers a maximum leverage of established simulation-based verification practices to emulation, including the benefits of using the system Verilog and UVM for creating modular, reusable verification component and environments. Related patterns. A precursor to this BFM proxy, a pair pattern in the dual domain hierarchy pattern, which advocated the HVL and HDL domain partitioning as a sound and a necessary separation of concern fundamental to emulation to other hardware-assisted verification platforms. Additionally, the BFM proxy pair patterns resembled the proxy pattern as one of the structural patterns of the GOF's OP design patterns, though the applying instead between a dynamic proxy object and a static interface or module. Pattern name: resource sharing pattern. Intent: the resource sharing pattern is categorized as environment pattern is used to share the resource between objects without requiring detailed knowledge of resource. Related resources share common access attribute, thereby creating a simple associations. Motivation: a hierarchy simulation environment contains resources required by other components as well as test writers. A consensus mechanism for sharing resources promotes horizontal and vertical reuse. A simple mechanism that requires no knowledge of the simulation environment hierarchy eases the task of test and stimulus creation. Applicability: the resource sharing pattern can be used when reusing verification component. It can also be used to reduce the overhead of adding test writers to a project. Structure: resource and sharing attribute and value. Implementation: the resource sharing pattern can be implemented using either the UVM_config_db or UVM_resource_db with an UVM. For the example below, the UVM_config_db was selected because of its simplicity of use and a use model available. The UVM_config_db has two methods for sharing, resource sharing, set and get. It also supports the generic scope use model shown in this example, as well as a hierarchy scope use model required to share specific resources with a specific object. Resources shared can include but not be limited to configuration object, virtual interface handlers, and sequencer handlers. The example: let us consider a DUT with various protocol interface ports. Each interface on the DUT is given a unique string identifier. For this example, let us give one of the interface ports the unique string, the identifier ingress data for port. This unique string identifier is used to field name attribute listed in the structure table. The all resources for that interface, including the virtual interface handle, agent configuration, and the sequencer handler are identified using the unique string identifier. The string table below shows the values used to provide and access the various resources associated with this interface. The required constructs are available to environment developers to share the resources within the environment. The test writer only needs to know the information in the table to access resources associated with the ingress data port on the design. No detailed knowledge of the environment hierarchy is required to write a test scenario. 5 is consideration of creating our pattern library. It's important to establish the usability goals early on when developing any type of online library. And since achieving usability goals often places constraint on the required infrastructure, that is one area requiring thoughtful consideration. Consequently, we chose to broadly identify the usability for our verification pattern library as a knowledge base that is easily discoverable, referenceable, and relatable. In addition to usability goals, we felt it important to set goals on the pattern creation process and how to effectively populate the library. On a related note, you might have wondered that why there is a large set of the authors listed on this paper, which we refer to as a GAN or 5. This reality is that verification is a diverse field and it often requires expertise in varied areas such as methodologies, technologies, tools, and languages. No single person is a master in every aspect of verification. Thus, to create patterns across the broad field of verification, we built a team made up from the experts in assertion-based verification, formal verification, constraint random and coverage-driven verification, UVM, hardware-assisted verification, and emulation. However, even with this diverse team of experts, we recognize that there is still additional verification expertise required for solving the verification problems in specific application domain. Hence, for our verification patterns library, we set a goal that a pattern creation process should harness the power of online social communities made up from the diverse set of the verification experts that work on multiple application domains. In turn, this community of experts would foster collective problem solving, the creation of novel patterns, and provide alternative optimized solutions for existing pattern content. To achieve these goals, we develop a web-based infrastructure that allows new content to be contributed in a consistent format, which follow the pattern template guidelines that we discussed in section 3. The final verification pattern library goal we set was to grow the user base as quickly as possible. For this goal, we decided to leverage the Verification Academy since it consists of an existing online social community with over 35,000 design and verification engineers. Furthermore, the Verification Academy provided us an existing online infrastructure, reducing our development costs, which enabled the creation of a patternology base that is easily discoverable, referenceable, and relatable, so that our freely available online verification patterns library can be accessed at verificationacademy.com. 6. Section 6. Summary and future work. As we stated in the introduction, pattern examples from previous publications are generally difficult to search, reference, and leverage since they are distributed across multiple heterogeneous platforms and databases and documented using multiple varied formats. So in addition, prior work in verification patterns has been limited to in scope by focusing predominantly on the coding aspect of simulation-based test benches. In this paper, we addressed these concerns by extending the application of patterns across the entire domain of verification, that is, from specification to implementation, and then introduce a systematic set of steps for organizing and documenting an easily referenced verification patterns library. Finally, we demonstrated our documentation format on 3 examples, which are representative of the class of patterns found in our library. Our current plans are to continue populating the library with new patterns, many of which will be drawn from previous publications. In addition, we are opening our pattern library up to an online social community to contribute one's own unique patterns to the library. Our future plans are continue exploring new applications of patterns in the emerging verification domains, such as portable stimulus and system-level analysis. Finally, we plan to explore a few additional scopes that leverage the expressiveness of regular expressions, which were not considered by the work of Droya et al. References as 1 to 14. Appendix: Verification Academy Pattern Library. The following table represented the Verification Academy Pattern Library released contents as of the time this publication. For an up-to-date listing of released patterns, visit the verificationacademy.com. Pattern name, category, subcategory, and description. Okay, today I read this paper, quite a long paper, the verification patterns taking reuse to the next level. Thank you for your time again, and see you next time.